Morning and welcome back again to the last session this week. And as we discussed yesterday, in connection with both efficient ways of implementing the Hartree-Fock algorithm, and then we discussed something which is called Thouless theorem, which we will use to make an analysis of the stability of the equations. And this is something which is, I shouldn't say straightforward, but it is doable in second quantization. And we can find a necessary but not sufficient condition for the stability of the equations. And what we're going to use then is actually Thouless theorem, which allows us to express a Slater determinant in terms of a reference state times an exponential which includes particle hole excitation. And that's the quantity which we also use when we now look at variations in the contributions from these particle hole configurations. So the topic today is actually to look at the Hartree-Fock equations. And if we get time, we will start looking at the homogeneous electron gas, which has been an extremely, and it still is, a very popular model for understanding properties of metals, semiconductors, and other materials. And it serves also as a testbed for many-body theories. So everybody who develops something new in many-body physics needs to pass the test of the electron gas, whether this is in 3 dimensions or 2 dimensions. So I'm going to switch quickly back to the whiteboard, and we are going to go through some of these, well, not too exciting derivations, but at the end, the reward is that we have a set of equations which we can use to get a first impression on whether the equations will converge or not. Okay, so let's switch to the whiteboard. So the topic of a large fraction of the lecture today is to look at the stability of the Hartree-Fock equations. So let's just have this as a header. So this is the stability of the Hartree-Fock equations. So what we found through variational calculus, and we are going to use this notation, which is a little bit more compact, where we said that the Hartree-Fock state is now given by this more compact notation C here, where C often refers to our core, which we can use as a reference state. So the variational condition which we derived says that delta C of H is equal to 0, and the equivalent equation is the other one of delta C equal to 0. And that's simply what this does. It finds an extremal value, but it doesn't guarantee that this is a minimum. So what we would like to do now is actually, given a random Slater determinant, we want to be sure that what we get here is actually a minimum. So what we did yesterday was to assume that we could have a perturbation of this original state plus some delta C. And what we did then was to say that this C prime, when we use Thouless theorem, is something which we can rewrite in terms of these particle hole excitations. So we had a sum of A and I, and then we have a delta CIA, or just CIA as we called it yesterday. And we think of this delta CIA as a small perturbation, where we now mix in particle hole excitations. So this is what we showed yesterday, that this is actually a general representation of a Slater determinant. Then what we want to show now is that if we calculate the expectation value with respect to this C prime, let me just be a little bit more careful with the, and the quantum mechanical expectation value includes also the norm. And what we want now is to be sure that if we make a perturbation from this Slater determinant, which we had, that this one is larger or equal to the expectation value of C, which we then define as E0 Hartree-Fock. So in order to figure out whether this solution which we're looking at is a minimum, we need then to guarantee that if we now look at this specific general Slater determinant, which includes now one particle, one hole expectations, is something which gives rise to a true minimum. So we know that from the variational calculus that we are getting an extremal value, but we're not sure whether this is the minimum value. So this is what we are setting out to do now. And what comes now is just a certain amount of not too exciting algebra. So let's go through this. And what we are going to do now, when we look at these expectation values and the norm, we are going now to run calculations where we truncate at the second power of delta C. So let's now see what we get now if we take the norm of the, or the denominator which we have. So if we take that denominator, C prime or C prime, if we write this out, what are we going to get then? Let's write out the wave function first, this C prime. So this will be given by 1, as we also wrote yesterday. And then we're going to have a delta CIA of AI of plus the higher order term. So we are just writing out the we have AI, and then we have a BJ, and then we have a delta CIA. There's a delta CJB, and then we have a set of operators, AI, AA dagger, AI, multiplied with AB dagger, AJ, and this goes up to infinite order in delta C, and this acts on the state C here. Now, if we now look at these amplitudes, we're assuming that these amplitudes are small, so we are looking at a small perturbation around the state. And typically what we would do now is to truncate at the level of the second order term. So we can actually, if we look at this norm here, we also know that when we calculate the norm, what we will get then is something which looks like this. So we'll get a 1 plus a sum over AI, and it's actually pretty easy to see that this is the case, and this is squared. And then we have higher order terms. And these are the terms which we are going to neglect in the evaluations here. It's actually pretty easy to see that, because if you calculate the norm of that specific quantity, C prime, you will quickly see that due to the commutation rules, which we have for the creation and annihilation operators, and the fact that these act on the reference state C, and you end in the reference state C, then the terms which we get have to behave like this. So there is no first order term, which you can quickly see, because then you will get a, if you take the first term, you would have this one multiplied with this, and that is obviously 0. So what we also see then is that chosen this specific, with this specific choice, this is not equal to 1, but what is equal to 1 is actually this one. Now, this is the denominator which we are dealing with. Let's look at the numerator. So in the numerator, that's a little bit more complicated. And if we now truncate the numerator at the level of delta C squared, so let's look at what kind of expressions we get when we do that. So now we are calculating the numerator, and we truncate this at the level of delta C squared. So the first term has simply to be equal to the standard reference energy, which we have calculated before. So this is just E0 ref. But then I'm getting now new contributions. So there's going to be a contribution from a state AI, a particle Hall state, and there's going to be a particle Hall state or excitation delta with BJ. So we'll have a CI complex conjugate of C delta CJB. And what I will have then will be a expectation value where I have an A of I, and this is as a creation operator, and then I have an AA, I have the Hamiltonian, and then I have my AB and AJ with C. So that's one second order term which I can get. Now keep in mind one thing, that since we have already required that this condition is fulfilled, that means that terms which involve just one delta C, either here or here, are zero. So that's why I'm starting with a term to the second power in delta C. Okay, so we just use the fact that we have performed the Hartree-Fock calculation. So with that, we have the next terms, which are going to look like 1/2, since we are stopping at delta C squared. So there's going to be a term of 1/2. And then I have a sum over AI. So I'm just listing this as particle Hall pairs. And I'm going to have a delta C AI, a delta C JB. And in this particular case, I'm going to have a expectation value, which I have to evaluate here, which is going to be given by AI, I always mix up AA dagger and AI, sorry for that, and AB, AJ of C. And then there is an additional term, which becomes the emission conjugate of this one. So I'm going to have a delta CIA, this is complex conjugate, a delta CJB, complex conjugate. And now I have multiplied this with C of AI. No, sorry, it's actually AJ. AI, but it's AJ dagger, and then I have AB, and then I have AI dagger, and AA of H with C. And obviously this continues with high order terms, but we are going to leave them. Now, let's now look at these different expectation or these transition probabilities which we're looking at, or transition matrix elements. So let's take a look at the first one and go through the algebra here and see what we get. We have actually calculated something like this before. So the thing we need to evaluate now are elements of this type. So I'm going to have an A. So if you look at the first term here, an AI. And then an A, B dagger, AJ, and C. So it's always useful to redo these calculations, because we did it some weeks ago when we listed up the matrix elements in full configuration interaction theory. But let's just remind ourselves, because to practice these things is always useful to do. So we have now two sets of operators. So we have the H, and then we have the one particle, one Hall state. And just to remind ourselves now, we have that H contains this E0 ref term. And we have the one body term. And we have the V interaction term. Okay. So if we now calculate the first one obviously will then require, since it's a constant, that A has to be equal to B and I has to be equal to J. So the first term gives us something which we have seen before. So we'll have a delta IJ over delta AB of E0 ref. And now we have to remember one thing, and that is that we have to multiply that one with these coefficients. So let's just leave these coefficients out and just look at, let us just look at the calculation of these transition elements. So this will be the first term. And then we have a plus, and if we take the term, so let's just do this term by term. So we have an A of AA, and then we have an AP dagger of AQ, and then we have an AB of AJ of C. So this term here has a sum over P and Q, and it's multiplied with the integral of P of H0 of Q. Actually, it's not H0, but it's the operator F, which in our case is the same as the Hartree-Fock operator, PQ, like that. Now, if we look at this one, you may remember that we had only two possibilities, which gave us something which is non-zero. So in that case, we could have Q being contracted with B, A being contracted with P, but then the whole states are just bystanding states which do not, which are not affected by the operator. And then the other possibility which we had is that we had AI being contracted with Q, and then we had P being contracted with J, and finally we had the two particle states which then have to be contracted with each other. So this term here gave us a delta AB, and then I have a delta P of J, and then I have a delta Q of I. And similarly, the other term gives us a delta of IJ, and then I have a delta P of A and delta Q of B. So as an intermediate step, when I collect all these things, what we got then is the term which goes like A of F of A minus I of F of I. And this is something which we will simply call the Hartree-Fock energy of the A minus the Hartree-Fock energy of I, the state I. And then obviously we have the different Kronecker deltas, which means that that specific term simplifies then to these whole energies multiplied with these delta C coefficients. Okay, so let's just bring them back at the very end. Now let's take the final term. So we have a plus of V of n here. And this is also something which we calculated earlier. So we have plus, and then we are looking at the anti-symmetrized integrals or matrix elements. We have a sum of all possible states, PQRS. And then we have the integral here in terms of what we call anti-symmetrized matrix elements. And this is multiplied with the contraction of A, I dagger, A, and then we have an AP, AQ, AS, AR, and then we have an AB and AJ here. Now, this is something which we found gave 4 different possibilities. These were the only possibilities which we could have. So let's take a closer look at that. So one clear contraction which we can make is obviously this one. Then we can do this one. And these are particle states. So that means that P and A give rise to a Kronecker delta, delta AP. And then I have a delta RB. So these are states above the Fermi level. And then the only other possibility is actually to take the operator and contract Q with J. So that gives us a delta QJ. And finally, the only operators left then are AI with AS, and that gives us a delta RS. So this is one of the possibilities. And since we now have these 4 possible contractions, when we now look at all the possibilities which remain, there are only 3 other possibilities. Now, when I do this now, what we have is actually two fermion lines which cross each other here in the contractions, and that gives rise to a minus sign. So this term here is going to give us, let's put this as an aside here, minus 1/4. And then I have a matrix element or an integral, A instead of P. And then I have my state S, the state Q, which is equal to J, which is this one. And then I have my interaction. And then I get my state B, which is equal to R. So that means that I have a B here, like that. And then the final one is R, which has been contracted with I, which has been contracted with the whole state. The whole state I, which has been contracted with S. So this is an I here. So what we get then is I, and this is anti-symmetrized. We can rewrite this in terms of a plus 1/4 of AJ of V of IB. And this is an anti-symmetrized matrix element. So we can actually choose whether we want to represent it that specific way or the other way. Now, as a small intermezzo here, since we're just doing an intermediate calculation, we can rewrite this in a diagrammatic form. So the diagrammatic form here would be a diagram of this type. So we have an outgoing particle state. We have an incoming particle state here. So that is a state which would then come in like this, an I here. And then we have a particle state which is outgoing. Now, so a whole state which is outgoing, so that is drawn as an arrow like this. And we have an incoming particle state to the right. So this will be the direct term. And then when we open it up, we would have a diagram which looks like this for the exchange term. So this will be an I, this will be a J, this is our B, and this is the A here. So this is are the two contributions. One is a direct and the other is the exchange one. But just pay attention now to that I actually interchanged I and B here. So you could actually redraw it, but then the direct term would be this one, and the exchange term would be that one. Now, the reason for why you often draw this diagram is that now you can think of this as a particle hole excitation which comes in, and then this particle hole excitation gets annihilated here, and then it gets created again after a given time t. Okay, so you can now perform other types of contractions. So what we could do now is actually to take I with R. That's another possibility. And then we would take S, so I with R here. And then we would have to do, we could do still keep that one. So there are three more possibilities. So that means at the end, what you get is actually a factor of 4 divided by a factor of 4. And you're going to essentially get the same elements. It's actually pretty easy to see that. So if I collect everything, what we will have then, when we collect it, we're going to get a Kronecker delta, which then simply becomes equal. So we have a Kronecker delta, delta IA, IJ, and delta AB, and this is multiplied with E0 Hartree-Fock. This is the reference energy. And then this now contains a delta C, since I is equal to J, I'm going to have a CIA squared. Then the next term which I get is a term where I have the same Kronecker delta, but now I have the single particle energies. So what I'm going to get then is an epsilon A, Hartree-Fock, minus epsilon I Hartree-Fock. multiplied with the same coefficient, CIA squared. And this contains a Kronecker delta where I have put delta IJ, delta AB. Then I'm getting new terms. So because my summations over A and B now have to be implemented again. So if you look back at the equation which we started with, which is this equation here, what I've done now is simply to require the Fourier contractions here that they get a specific form, but I'm going to have a sum over these quantities here. So I have a sum over A and B. I have a sum over I and J. So that means that when you look at that specific term there, we have to be a little bit careful because this means that we have to make a sum here over A and I. Okay, so that is that term. And then when I add these different matrix elements in addition, for the contractions which you have with the Hamiltonian, with the two-body interaction, what we then need to do is actually to plug in the expressions here. And in that specific case, we're actually having a sum over AI and BJ. So what we're going to get at the end is plus a sum over AI and a sum over BJ. And then we're going to have these coefficients, CIA, complex conjugate, and delta C, JB. And then we have this matrix element, which is given by A of J, of V, of I, and B, anti-symmetrized. Okay, so that was that term. Then let's look at the two next terms. And one is just going to be the Hermitian conjugate of the other one. So it suffices actually to calculate only one of these terms. So let's now look at the next term, and now I'm going to make this a little bit, I would say, faster. So we have a C of H, and then we're going to have an A dagger, AI, and then I'm going to have an AB dagger of an AJ acting on C, and then we have these coefficients, either complex conjugate or just the other one, which is not complex conjugate. But let's leave that out and let's look at these expectation values. Now, one thing which we see immediately is that the term here with the reference energy has to give 0. Because what we do here is that we create a two-particle two-hole state. And then with a constant here, we have nothing which can bring us back to the vacuum state. So that has obviously to be equal to 0. So we can just set that immediately. So this term here is equal to 0. Then let's now look at the one-body term, because that's also quite interesting. So, and let's now just write it out without all the summations and all the integrals as well, just to make life a little bit easier. So this is also a term which is going to be simplified considerably, because what we see now, if we think in terms of excitations, so let's take a closer look at that term. And so we have a C, and then we have the one-body operator, and then we have the, I'm just rewriting it. Now, what we are creating here is actually a two-particle two-hole state. This is essentially what we have. Now, if you then look at the operator here, this operator can at most take out one particle, one hole excitation. So that means that when the operator is being contracted with one of these states here, let's suppose we have this contraction and then this contraction, we are left with two operators, which will give us a one particle, one hole state. And then we just have to go back to the reference state, and there is nothing which can bring us back to the same state. So that means that the one-body operator gives us exactly 0, because we cannot, we don't have any features in this operator here, which creates a two-particle two-hole state. Whereas what we start with is something which is a two-particle two-hole state. So this term here is actually equal to 0. So the only term which gives us something which is non-zero is the two-body operator. So let's just write that out without the summations and without the integrals which we are going to put in at the very end. So there's going to be a term which looks like this. So there's going to be an AP, an AQ, AS, AR, and then I have my AA, AI, AB dagger, AJ. Now the A's and I's and B's and J's, they are fixed to be states either above or below the Fermi levels. The PQ, R, and S are free states, so they can be both below and above. But due to the anti-commutation rules, which we have and the way we have defined contractions now with respect to the new vacuum, these guys here leave us only with some few possibilities. So one possibility is this contraction here. And then we could have this contraction here. So this is a contraction which is non-zero. So these are particle states. So that means that S and R become then particle states. Then what I could have is this contraction here. And finally, I could have this contraction here. So in this specific case, I'm going to get a minus sign because the matrix elements actually now, so this is going to give us 1/4. And then when I bake in all the Kronecker deltas, I'm going to have a J of I. So Q goes to I and P goes to J. And then I'm going to have a matrix elements AB of AS. But since I need to interchange at least one operator here to get every operator close to each other, this is going to have a minus sign. But I can rewrite this one as 1/4 of IJ of V of AB anti-symmetrized. So that's one possible contraction. Now, the next thing I can do now is to actually keep these two fixed and simply change these two. And that will actually give rise to this IJ element plus a minus sign, so I get a plus again. The next thing I can do now, I can keep these whole states, the contractions here fixed, and then I just change that one. And then I keep this one, which I've changed, but I change this one. So I'm going to get only 3 more terms. So in total, this term here is going to give us IJ, V, AB, anti-symmetrized. And these are the only contractions which can take place. So one way which is very nice when you're dealing with these operators is looking at the states. Look at the states as we do here. We create a two-particle, two-hole state. And since we only have a one-body operator and we are calculating a vacuum-to-vacuum expectation value here, then this case here has nothing which can be matched in the operator so that we actually back to the vacuum state. And then this is a typical case when you gain some intuition here, you can actually just look at these set of contractions and say, we know that this has to be 0 because we are trying to match a two-particle, two-hole excitation with something which at most can produce a one-particle, one-hole excitation. And that has to be 0 when you're looking at the vacuum-to-vacuum transition. Okay. And then the only one which remains to look at is the one which comes from the two-body operator. So what we have then is that this specific case takes a value which, yeah. Yeah. No, because you start with a two-particle, two-hole state. But if you now just look at the operators which you have, so if you look at the operators, what you would have then, if you just think of this as a set of operators, you would actually have what you could call a vacuum-to-vacuum expectation value with these operators. But that has to give you 0. But in principle, what you're doing is that you are in a two-particle, two-hole state, and you want to go back to the vacuum state, and there is an operator here which gives you at most a one-particle, one-hole excitation. With the operator here, what you have is a two-particle, two-hole state, and then you can, with this operator, you can create a two-particle, two-hole state, and they match each other. So the matrix elements which you see here are matrix elements which I'm now going to just slightly rewrite a little bit. So if you now take the other term, so there's going to be a term, the final term is going to be of this type. So there will be an AJ dagger, an AB, an AI dagger, an AA, and then we have the Hamiltonian. And if we just use the properties, which we know that if we have a Hermitian operator, we know that this one, if I take B of A dagger, so these are just the random states, you know that. If we use that, what we can say now is that if we collect these terms, we have a C of AJ, AB, and when I do the contractions here, I'm going to get something pretty similar to what I had previously, except that this one is going to be given by, that will be, sorry, no, I have to be, just a moment here. Yeah, this one is going to give us an AB of VIJ. And what I can do then is simply to rewrite that one in terms of IJ. So this is anti-symmetrized. Of VAB, anti-symmetrized, and then just a complex conjugate of that one. So what we can do now is actually to define the final set of operators which we have, or the set of expectation values. When we bring this back now, what we have for this specific term, if we now collect everything, we have the term C of HC, that contains a 1 plus, yeah. Yeah, but the V is already, it's just a real quantity normally, so that is Hermitian. So you don't need to do anything there. That is just by assumption. Now, if you then look at the terms which we have, if we now start collecting, what you get, if we go back here, you saw that we got a term here which contains this E0. So from this specific, if you look at this specific term here, that one gives rise to a term which contains E0. But that E0 term needs to be multiplied by these coefficients. So I can write this up when I'm putting this up. I need now to have a summation over A and I. And then I have a delta CIA squared. So that's that specific term. Then I get a new term here, which is given by a sum over AI. And then I have my delta CIA squared. And then I have the Hartree-Fock elements, A Hartree-Fock, the energies of H Hartree-Fock. And my next term is now going to be given by plus, so we have a sum over AI, and I have a sum over BJ, and then I'm going to get a delta CIA, a delta CJB, and then I have this matrix element, which I had as an A of J, of V, of I, and B, anti-symmetrized. And then I have two additional matrix elements. And so that means that I have a plus, I have a 1/2, and there's a summation over AI, a summation over BJ. And then I'm going to get a delta C IA, a delta C JB. And this is multiplied with the matrix elements IJ, VAB, anti-symmetrized, plus 1/2. And then I have my AI, BJ, but now I have a delta CIA, complex conjugate, delta C JB, complex conjugate, and then I have my AB, VIJ, anti-symmetrized. Now, what I can do now, if you now remember that this term which you have here, this one is nothing but our reference energy, E0 ref. So what I get then, when I look at the numerator, I get something which is now, which I can now write as a 1 plus, and then I have this AI of delta CIA squared multiplied with E0 ref, or E0 Hartree-Fock, which is the one I use now, E0 Hartree-Fock, plus, and then I'm going to put all these other terms in a common container, which I call delta E. And if I want to be a little bit more picky, I should actually have now an O of delta C of AI cubed, if I'm not putting an approximation sign. Now, remember now that the numerator is given by that, but then we have the denominator. And if we now denominator, and the denominator, when we stopped at the level of delta C squared, we had that the denominator was given by delta C squared. We can then rewrite this because you see now that the denominator, if that is given by that term, that would simply cancel what you have here. And that means that this expectation value, which we are looking at, this C prime of H, of C prime, divided by C of C here, this is something which we now can rewrite. And this is now we are approximating this to only include delta C squared. This becomes simply E0 Hartree-Fock, plus these terms which we have laboriously calculated, delta E divided by 1 plus this summation over AI, and then have a delta CIA squared. So what I wanted now is to show that this E0 Hartree-Fock is the minimum. In order for that to be the case, what we need then to fulfill the condition that this is a minimum, then we simply need that delta E is larger or equal than 0. So we set out with the proving we want to prove. So we haven't proved that this is the case because it depends on the expectation values which we are looking at. Not that one, but delta C. So we want to show that the Hartree-Fock energy which we have calculated is a minimum. And the condition which we have here is that this delta E has to be larger or equal to 0. Yeah. So we don't know whether it's a global or local minimum. So then you would have to have a handle on whether this is a convex function and that it guarantees that it's a global minimum. So the only thing we can guarantee is that it is a minimum. But we don't know whether it's a global or local one. That's a very good point. But we are hoping that this is a global. But then we have a condition here, and after the break, what we're going to do now is actually to rewrite these equations in terms of a matrix. Because you see now that we have these coefficients here, which we are going to rewrite since we have these explicit summations we are going to rewrite these as vectors times a matrix times a new vector. And then the matrix which we're going to set up will contain as matrix elements these different integrals. And that means that when we set this up as a matrix, this delta E, then we know that for this to be true, to be fulfilled, the matrix has to be semi-positive definite, which means that the eigenvalues of the matrix have to be larger or equal to 0. And a sufficient but not necessary condition, which you can use in order to see whether this is hopefully the case, is to look at the diagonal matrix elements. And if they fulfill that condition, then we know that the Hartree-Fock calculation will be stable. So after the break, we are just going to rewrite this delta E in terms of vectors containing these coefficients and a matrix which contains the different integrals. And then we will have the final sufficient but not necessary condition. No, necessary but not sufficient, sorry, condition. Yeah. Okay. So what we're going to do now is to rewrite these equations a little bit, and we are going to introduce a more compact notation. And the notation, if we now look at, for instance, the term which we call delta C of H delta C, which we found to be equal to, so let's just write it out, AB IJ. And then we had, and now what I'm doing, I'm going to skip the reference energy. So let's just skip the reference energy because that comes just as a constant in addition to that. So we had a delta CIA. So the analysis here now, because we are now interested in that matrix delta E, which we had here. And if you go back to the equations, you see that E0 is something which we can pull out. So let's just leave that out here in the equations. And we have a Cj of B. And if we now write it out, this term, we have an epsilon A, Hartree-Fock. And then we have a delta AB, delta Ij, minus an epsilon I, Hartree-Fock. And then again, a delta AB, delta Ij, like that. And then we had the two-body integrals, or just two-body matrix elements, as we've been calling them. And this is given by A, J, and V, and then we had this I of B here, anti-symmetrized. Now I'm going to introduce a little bit more compact notation. So I'm going to define this in terms of particle hole configurations. So I'm going to introduce a label I, which now is going to stand for the states AI. And then you see that I can replace the summation of AI with I. And then I'm going to have an uppercase letter J, which is now going to contain the other particle hole state which we generate here. Now, if I do that, then I can rewrite the matrix elements, and I'm going to also redefine this matrix element, or integral as we call them, AJ, V of IB. I'm going to call this for a quantity A, and this is going to depend on the particle hole state AI and the particle hole state BJ. And I will just rewrite that as an AIJ here. So you see now this kind of matrix notation being sneaked in. So that means that my delta CIA is just going to be given by delta of CI. And similarly, my delta CJB is going to be a delta C of J. And then I can do the same thing with these single particle energies. So I'm just going to define a new quantity, which is this delta epsilon J, which is equal to epsilon A Hartree-Fock minus epsilon I Hartree-Fock multiplied with delta AB and delta IJ. Then I'm going also to introduce a new matrix element, which I'm going to call for B of IJ. And this is going to be given by these elements, which we had for the second term. So this is going to be given by a matrix element AB of Vij. And that means that they have a Bij, which is going to be Ij of VAB antisymmetrized. So if you then look at what we had previously, when you look at these different matrix elements, we had now these coefficients. We have this matrix element here, and then we have this matrix elements here, which we're going to relabel as B and B here. And then the term which you see here, something which is going to be relabeled as an A. And then I need just to pay a little bit attention to these quantities here. Now, if you just take the first term, the one which we started rewriting, so this term here, delta C of H without the Hartree-Fock energy, is something which we now can rewrite as an Ij of delta Ci and a delta Cj multiplied with delta epsilon Ij, and then I have a delta Ij here, plus this matrix element Ij here, like that one. And just keep in mind that when we look at this quantity here, the way you can also think of it is as follows. So if you think back of a matrix vector multiplication like this one, this is nothing but a sum of Ij of Xi, the specific matrix elements Aij, multiplied with Xj. So when you look at this expression which you have here, this is something which we now can rewrite in a more compact way as a vector delta C. So this is actually the transpose, if this is a real quantity, multiplied with a matrix which we can call for delta E. So that would be a matrix which has only diagonal elements, times a delta C plus this delta C multiplied with this matrix A times delta C. Now, this is now going to be the way we are going to rewrite this whole quantity delta E. So with this kind of definitions, what we are going to say now is that this delta E is going to the total delta E, which is the quantity we have calculated here, which contains this term, and these terms which you see here, except for the reference energy, which we now have pulled out. So if you look at this one, we are going to redefine it in terms of 1/2, and you will see that when you do the algebra here, this is going to be correct. So I'm going to put up this vectors chi here. So this vector chi is something which I will define as one part which contains delta C, and the other one which contains the complex conjugate one. And the matrix M, so when you write this out now, you will see that this actually gives back the original equation. So this matrix M is now this delta epsilon plus A. There's going to be a delta epsilon plus A complex conjugate, and then I have this B, and then I have this B complex conjugate. So that means that when you look at this quantity here, in particular, if you look at the diagonal elements, so when you write this out, you will see that you get back the original equations which we defined. Now, the thing which we require now for delta E to be larger or equal than 0, then M has to be semi-positive definite. Which means that the eigenvalues have to be larger or equal than 0. So its eigenvalues, its lambda i's, have to be larger or equal than 0. So a necessary but not sufficient condition is that the diagonal matrix elements are larger than 0. So that means that a necessary. So this is something which you can do in order to inspect a matrix if it's positive definite or semi-positive definite, is to look at the diagonal elements. So instead of diagonalizing the matrix. So necessary, but not sufficient. Condition is that the diagonal elements is that epsilon A Hartree-Fock minus epsilon I Hartree-Fock plus this matrix element, which now is the diagonal one, which then would contain an AI of V of IA, that these should be larger or equal than 0. So that's quite interesting, because then you can look at the single particles energies you have and relate them to the strength of the interaction. So that gives you quite a quick handle if you have these quantities. Then you can say something very quickly about whether a Hartree-Fock procedure will converge or not. And that's an extremely, how to say, powerful way of actually studying the problem here. So what we have done, if we collect all these bits and pieces here, and we link this with FCI, so what, in FCI what we had, just let us quickly summarize a little bit. So in FCI what we end up calculating is a matrix where we have the vacuum to vacuum expectation value, which we bring back now in the old notation. And then we have a one particle, one hole block of H, phi 0. Then we have the two particle, two hole block, H with phi 0. And this goes on to the n particle, n hole excitations we can make. Then we would have now again here a, this is actually, I just need to rewrite it a little bit. It's the opposite. So the next block here, phi 0, H of one particle, one hole. And then I have a phi 0, H of two particle, two hole, and etc. up to the n particle, n hole. And if we have a two-body interactions, all terms beyond the third one here are 0. This is the one particle, one hole block. We have the two particle, two hole block, H of phi 0. Here we have a one particle, one hole block. This continues and all the way down here. Now, when we did Hartree-Fock now, with the Hartree-Fock basis, what we do then is that these matrix elements are zeroed out. And we reshuffle some of the strength over to the other matrix elements which we have here. And so a Hartree-Fock calculation, as we have seen now, we have a variation, a delta C of H with phi 0. We can just call it a phi 0 here, which is equal to 0. And that leads to, in our specific case, when we translate these many body states into explicit expressions which have to be fulfilled, and when we have built the basis with a set of single particle states which define our Slater determinant, then this leads to the condition which we have here. So we have an A of an F of I equal to 0. And this classical way by which we implement this, so the classical solution is then to assume that this Hartree-Fock operator is equal to F, which means that when this H Hartree-Fock acts on one of these states, P, this is equal to epsilon P Hartree-Fock, or P here. And that's a way by which we can implement I of F of A, which is now equal to I of H Hartree-Fock of A equal to 0. And then I have I of H Hartree-Fock of I, which is equal to the Hartree-Fock energy for the states below the Fermi level. And similarly, we have for the states above the Fermi level, Hartree-Fock. So this is the classical solution. Now, when we now are moving to the electron gas, you will also see another way by which we can implement these conditions. So when we now move into the electron gas or the homogeneous HEG, the homogeneous electron gas, then what you will see is that for the states above the Fermi level, the standard approach is to put that one equal to 0. No, sorry, it's to put that one equal to 0. So it means it's only the states below the Fermi level, and that will create a gap above the Fermi level. Now, the other thing which we saw is that these single particle energies, which we define here, can then, through Koopman's theorem, which relates the binding energy or the energy differences between a system with n particles and n-1 particles, or n+1 and n particles, then we could show then, if we assume that the single particle states are the same in the two systems, then we could show that these differences are either given by the whole energy or the particle energy of the last removed particle or the last added particle. And that gives us a nice connection for Hartree-Fock theory with experiment. And for atomic physics, this actually works pretty well. Now, there's one thing which I want to do as a minor digression, and that is to use this way of thinking, which you have from the FCI, to derive another method, which is called the Tamm-Dankov approximation, which is a way to find the coefficients for the particle Hall states by solving an eigenvalue problem. And later we will see how we can calculate this specific approximation using Green's function theory or many-body perturbation theory or other many-body methods. So let's just, before we begin with electron gas, let's do a small digression. So this is called TDA. So this is Tamm-Dankov. And there are many ways to derive this. And let me find my other notes here. So this is something which is pretty close to what we did with the Hartree-Fock equations. So if we now look at the matrix elements which we have calculated in Hartree-Fock theory, so what we found is that this A of F of I is something which we've been putting to 0. Now, when we go back to the FCI equations, you may remember for some 2 or 3 weeks ago that we looked at the equations for FCI. Instead of a diagonalization approach, we multiplied from the left here with the either phi 0 here, and then we got an expression for the reference energy. So let me quickly set this up. So we found that this reference energy could then be written as delta E in terms of a correlation energy, which was given by the exact energy minus the reference energy. And the reference energy, just to remind you of that one, is given by phi of h of phi 0. And this is something which we then could rewrite in terms of a set of particle-hole terms. So when you diagonalize, you do actually have these terms. So this was given by an I, and then we have the operator F, plus a two-body term, A, B, I, J, and then we have the coefficients which we get from diagonalization. And this is something which we have only if we are dealing with a two-body interaction at most. So this is an exact expression for the correlation energy. And these are all quantities which we either can calculate by diagonalization, and if we diagonalize, we actually get these terms. Alternatively, we are going to find approximations to these terms. And you will see that after we've done Hartree-Fock theory, you will see that these coefficients are going to be given by, let's say, many-body perturbation theory for second order. We give you a expression for these in terms of the single particle energies and the matrix elements. We can use copper cluster theory to find an approximation to these coefficients. We can use Green's function theory and many, many other many-body methods. Now, if we did a Hartree-Fock calculation, then we found that this one is 0 if we have a Hartree-Fock calculation, but it's not necessarily equal to 0. So this was in case we multiplied, if we go back to the equation we have here, if we multiply the first row here with phi 0, and then we get obviously this term, we get this term, which then becomes 0 if we have performed the Hartree-Fock calculation, and then we have the final term here. And since we have a two-body interactions, all the other ones are 0. Now, the other thing we did was to multiply with a phi IA here, just one of the particle-hole configurations, but keep in mind that we have a whole block of one particle, one hole configurations here. But when we did that for one of those, what we found was, if we now look at that, so let me quickly remind you what we got there. So there were matrix elements which we actually calculated in the previous lecture, where we needed to calculate this. If we now stop, so we have these matrix elements here, CJB. If we look at that one, so we multiply from the left, and there is a term which now contains the reference energy and also the exact energy, which we want to calculate. And this specific element here, so on the left-hand side, we have the energy we want to find. But this specific term here, when we calculate it, this is obviously given by E0 ref. And then I have my CIA, and I have a delta, as we did before, of B, plus, and now I'm not specifying whether these are Hartree-Fock states or not. You can put these as Hartree-Fock states, but just let's leave them unspecified. So delta AB multiplied with CIA plus a sum over JB. And then we have the matrix elements AJ, B, IB, anti-symmetrized, multiplied with CJB. Now, this is not the whole picture, because what we have neglected now is, so we have neglected when we multiply, so what we did was actually to multiply with that state. So we have H minus lambda of all the one particle, one hole states. So what we did was simply to take this row here, this one, and multiply with the one particle, one hole states. There's going to be a contribution like that one. So if we have performed the Hartree-Fock calculation, the first term will obviously be 0. But then we are going to have a one particle, one hole state, which gets multiplied with that. But there is also a part which is multiplied with a two particle, two hole. and there will be a free particle free hole. So if we now put this one to 0, and also the one with a free particle free hole to 0, then we know that if we have performed the Hartree-Fock calculation, this term is 0. But then we are just left with this term. If we now say that the coefficients Cij AB and Cijk ABC are 0. So that leaves us only with the evaluation of that specific term. And this is something now, because this is going to be equal to some lambda multiplied with this coefficient CIA. So I can then shuffle this delta E ref to the left-hand side, because if you look at the equation which we have, what we are going to do is exactly the same as we had here. So we replace simply this E0 with a lambda. And we get an equation for this E lambda minus E ref, which is now going to contain these single particle energies. But these single particle energies is something which I now can bring together inside a new Hamiltonian matrix. So what I'm essentially requiring is the following. So I'm going to have a summation over JB, and then I have a phi IA of H minus a state lambda of phi J of B multiplied with a CJB, and we want that one to be equal to 0. And now I have put, without knowing whether that's correct or not, but I put these coefficients ABC to 0. So that's an approximation which I'm making. Now, if I do this and plug in what you have here for that specific matrix element, I can actually rewrite this equation in a very compact form. And the compact form now, if I define again a new matrix as we did before, so I have this matrix A of Ij AB, which is equal to Aj of V IB anti-symmetrized. And then I have my delta or delta epsilon. And then remember that we actually transform this one into an Aij, where I is now equal to AI, and J is equal to Bj. Then I could similarly have a term which we call delta Ej, which was simply given by epsilon A minus epsilon I, multiplied with delta Ij and delta AB. So if I bring together these terms, what I will have then is this term here will have a term lambda, which is a constant, and that picks out a case where I has to be equal to J and A equal to B. So when I do this rewrite, what I will get, if we now define this delta E as this lambda minus the reference energy, so which I have from this expression here, then if I do that, I can rewrite everything as a sum over I and J, and no, sorry, just J. And then I have the delta epsilon Ij plus this matrix elements Aij multiplied with the coefficient Cj. And this is simply going to be equal, since I have on the other side, I have the configuration AI. This is going to be equal to this delta E times C of I. This lambda does not need to be the ground state. It could be another state. And that means that the coefficients would correspond to an excited state. Now, what you see here is an eigenvalue problem, which I can now redefine a new matrix which I could call for Hij. And then what you see is that this is the same as the sum over j. I have Hij multiplied with this coefficient Cj, which is now equal to delta E of Ci. So this is a way to find the eigenvalues for the one particle, one hole states. But where you made an approximation where you're not mixing in any two particle, two hole or three particle, three hole states. So this would correspond in principle to the eigenvalues. And just keep in mind that we have subtracted the reference energy. So it's the relative energy of the to the eigenvalues of the one particle, one hole states. Now, when you are solving this eigenvalue problem, what it means is that you are summing this one particle, one hole excitations. When you diagonalize, you're summing them to infinite order. Now, you can diagonalize this problem, or as we will see later, we can actually rewrite this one as a Green's function series, which we can resum to infinite order. So if you do Green's function theory, or you do many-body perturbation theory, where you can resum specific terms to infinite order, that is equivalent with you diagonalizing a problem. So this is now a reduced problem, where we simply assumed that the coefficients which link with two particle, two hole, and three particle, three hole excitations are just put to zero. So it's a cheap way of getting the energies of the one particle, one hole states. And this is normally called the Tam-Dankov approximation. You can then mix in two particle, two hole excitations, and then it's called the random phase approximation. And we are coming back to that one a little bit later. So this was just a small digression on how you can actually approximate the full diagonalization problem. So in this specific case, what we have done is to neglect for the calculation of the excited states, which we now reduce to be only one particle, one hole states. We have simply neglected all these other terms by construction. If we run a Hartree-Fock calculation, we are left with these terms. And what this means, what we did, is that we are diagonalizing the one particle, one hole block. That's actually what we are doing, because keep in mind now that when you run a Hartree-Fock calculation, then these matrix elements get changed. These matrix elements get changed. We haven't zeroed out these ones. But if we don't want to diagonalize the full matrix, we can now just diagonalize the one particle, one hole block, ignoring these ones. So we are simply ignoring the contribution from two particle, two hole excitations. And that is a way to approximate the full diagonalization problem. Hartree-Fock theory is also one way of making an approximation where we zero out some specific matrix elements. We get a better basis. And we are obviously hoping that this condition is fulfilled so that the Hartree-Fock algorithm gives a stable solution. And then we can make further approximations to the diagonalization problem. Obviously, if we can diagonalize the whole matrix, then we do have these coefficients immediately. But in general, the matrix can be pretty large, and this is just beyond what is feasible to do. And then we need to find approximations. So this Tam-Dankov approximation is actually one of the standard approximations which many people actually run. I think we stop here instead of beginning with the electron gas, because we have something like 5 minutes left. So what this does is that it concludes the general theory for full configuration interaction theory and the Hartree-Fock theory. Next week, we are going to look at an example of where we can find the analytical solution for the Hartree-Fock approximation. And this is the electron gas. And the electron gas is also going to serve as a motivation for calculating something which is called the exchange correlation energy, which is used in density functional theory. So next week, in addition to introducing the first midterm, we will mainly focus on Hartree-Fock theory applied to the homogeneous electron gas. And then afterwards, before we begin with perturbation theory and other methods, we are going to look at density functional theory, which is also a very popular many-body method, which is widely used in material science, in atomic physics, and also in nuclear physics and in molecular physics or quantum chemistry in general.